Hello, everyone, and thank you for joining the webinar. Today, we're going to be taking a look at several geodata options and how they can be applied to improve the reliability of planning for the next generation of broadband networks. As we move into 3.6 gigahertz up to the millimeter wave frequencies, which become much more dependent on line of sight, the improved granularity of geodata used to model the environment is going to be critical in planning these networks reliably. In a moment, Brian Jones from EDX will walk through some of this data, and we're also joined by Andy Baffis of EGS Technologies. If you do have any questions during the webinar, you can input those into the webinar panel on the side of your screen, and we will answer them towards the end of the webinar. And now I'm going to pass the floor over to Andy Baffis.
Thanks, Rory. Hello, everyone. Let me first say welcome to all the participants in this webinar, and we appreciate you taking the time to learn more about the improvements in geodata for use in RF designs. Also, a very sincere thank you to EDX Wireless for including EGS in this presentation. First, a little bit about EGS in case you don't know about us. Our goal is to support RF engineers with their geodata needs. We not only provide geodata, but also offer consulting services to clients who need additional support with conversion, reprojection, or analysis of mapping databases. The year 2020 represents our 25th year of business supporting the mobile telecommunications industry, and we're thrilled to reach this benchmark. Our corporate ownership is based on individuals with academic backgrounds in both RF engineering and geography, so we're well suited to understand the needs of the industry. And given our size, we remain nimble and able to adjust to the ever-changing requests from our client base. To support that goal, we also partner with a number of third-party suppliers to assist us in the creation and delivery of geodata. Combined with our experience with projects on 6 continents over our 25-year history, we are honored to be able to partner with EDX Wireless and their customers. It has always been our corporate goal to minimize costs for clients, improve data quality, and reduce delivery times for geodata products. EGS offers a number of geodata options to our clients to help meet that goal. Firstly, our 2D or two-dimensional data includes data layers of clutter, terrain, and linear vectors. It's considered 2D because it does not offer any discrete vertical measurement for the clutter layer. Our lowest cost option, data of this category, is available from archives in various resolutions, both within the United States and internationally. Historically, generation of a vertical measurement for per bin clutter was a time-consuming or cost-prohibitive process. That is changing with improved processing technologies and increased satellite image granularity. 2.5D is the direct beneficiary of these improvements. By adding a clutter heights layer, a per bin vertical height is provided for your area of interest with our 2.5D product. Clutter heights can add significant improvement to predictions over larger suburban and rural regions. EGS currently offers a 10-meter resolution clutter and clutter height data product nationally, derived from recent imagery sources, offering a great value to clients who want this improved accuracy. Custom regions and resolutions are also available at a client's request. Additionally, our 3D databases offer our highest accuracy geodata option. They include unparalleled detail in the vertical and horizontal dimensions with resolutions to 1 meter. It includes 3D building and vegetation vectors, along with the standard clutter, terrain, linear vectors, and raster clutter heights provided in the 2D and 2.5D datasets. 3D data is available for both client-derived and archived areas. This data represents our highest quality and accuracy product. EGS also offers supporting data layers like socioeconomic data, population counts, location-based social media layers, and other spatial databases. Our goal is to provide a vast array of geodata layers at resolutions and pricing that meets both the budgetary and project requirements for our customers. I'd like to now turn it over to Brian Jones of EDX Wireless to show you some of the real-world applications of the geodata EGS offers within their software.
Thanks, Andy, and thank you everybody for joining today. Again, my name is Brian Jones. I'm a customer success and sales engineer with EDX Wireless, and my main focus is on how our users are leveraging their geodata within Signal Pro and leveraging the features of Signal Pro to effectively plan their different networks and evaluate the different use cases that they may have to plan in the tool. What I'd like to focus on today are sort of three different use cases specifically for 5G, and especially the mmWave use case. The geodata options that we're discussing today, of course, are applicable to any technology or any sort of network planning needs. But I'll be using use cases from 5G just as an example to talk about sort of the trade-offs between the different approaches that you might have for RF prediction. And so the question arises, with all of these different options available to represent the physical world in my planning tool, which data set is right for the needs of any particular project? You know, users working with Signal Pro may be building projects in sort of an initial dimensioning capacity where you need to find the number of towers to cover your fixed subscribers or your area. Or users might be really delving into a full network plan where you need to carefully place all assets and do channel planning and guarantee data rates to different subscribers. And depending on sort of what the needs are of the prediction in that sense, one data set may recommend itself just because of the affordability and the flexibility of having it available all the time versus needing to get higher resolution, more granular data for a detailed network design. So the three use cases that I'd like to talk about within 5G are sort of the low, mid, and high frequency band options that will be available under the 5G standard. The frequency bands that will be available are the traditional cellular and LTE frequency bands, less than 1 gigahertz, the 900 megahertz band, 700 megahertz, and the geodata and planning standards for that frequency band and that style of planning, those are pretty well established. You know, the industry has been planning at those frequency bands for a long time, and very often 2D clutter, such as the EGS hybrid clutter, or like the clutter that EDX offers in our Cirrus subscription data currently, that high resolution 2D clutter data is detailed enough and has enough information about the clutter heights just implied with the average heights for each category that planning can be done very reliably with 2D clutter data. If we start to look at the mid-band or high band of 5G, those being 3.6 gigahertz or mmWave, which is anywhere from 20 gigahertz on up to 60, 70 gigahertz, there are a couple of things that come along with that jump in frequency. First of all, the technologies all become much more line of sight dependent. At these higher frequencies, you do not get good diffraction around obstacles or necessarily good reflections and multipath to a particular obstacle, or around a particular obstacle to a receiver. So the higher frequency implies a need for more granularity and more detail in the height data so that you can guarantee line of sight, particularly for fixed subscribers. So in the case of mmWave fixed delivery, like to homes or businesses, that use case especially really requires a careful treatment of the height along the path in order to guarantee line of sight. One of the things that's also happening with mmWave delivery, both in the urban environment and in suburban and rural environments, is that the cell sizes and tower heights are becoming smaller and lower. Towers are closer to the ground, cell sizes are smaller. In the urban environment, that's because we're doing small cell delivery, and each cell only covers a small area so that it can deliver high capacity. And in the case of, for example, the Rural Broadband Initiative and delivering broadband to homes, the tower heights are often lower because we're using existing infrastructure from the utility poles and that sort of thing, as opposed to traditional cell towers. And so given that those tower heights have come down closer to the surrounding clutter, it's more important to have a granular representation of the clutter height along the path for the mid and high band cases in 5G. And there's been a lot of talk within the industry about what level of detail is necessary for planning of mmWave in the industry. And so far, from what I've seen, a lot of that talk has been focused on the dense urban core environment or high capacity environments. And one of the other areas of interest that we want to address is the suburban and rural case with 5G and particularly mmWave. There are a lot of opportunities there with the Rural Digital Opportunity Fund, and we've been hearing a lot from many of our customers, a lot of questions and interest in how can we establish best practices for planning these mmWave technologies in suburban and rural environments. So one of the points I wanted to make about using 2D clutter for planning these higher bands is that, especially for dimensioning purposes or pre-planning purposes, the 2D clutter, such as our Cirrus hybrid data, can still be perfectly appropriate for initial dimensioning of mmWave systems or mid 6 gigahertz, provided that you take extra care to go in and adjust the height associated with each clutter category for each market that you're planning in. In a 2D clutter case, each land use type or each category has an average height associated with it, and the propagation model will treat all clutter of that type as being effectively the same height. And those values given in the default file are going to be averages across, the whole country, and probably conservative averages that are a bit high. And so if you want to use that data for planning the 3.6 gigahertz or mmWave cases, it's important to look more closely at your market area and establish reasonable average values for the developed categories and for your foliage categories, so that you've got a reasonable model to start with for these very height critical links. If you wanted to step up the data set that you're using, though, full 3D data is often cost prohibitive for a larger market, and building polygon data is often not really relevant for rural planning, and indeed not available without, you know, substantial investment to go out and develop those building polygons and heights and everything. So it, you know, what's needed is a middle ground where we have a data set that gives the height for the clutter at each location, but is not necessarily a polygon representation of every building, and is something affordable and deliverable within a reasonable time frame. For those use cases, we've found the 2.5D data to be a really ideal alternative that suits these use cases very well. Before I move on and show you that data and do a comparison real quick, I want to talk about the propagation model that we're using, particularly in, or specifically in Signal Pro, to do this type of planning. Anderson 2D is by far our most popular and widely used propagation model. It's a terrain-sensitive model, or a diffraction-sensitive model, that will first evaluate the path to determine whether it is line of sight. And if there is an obstruction, it will add additional path loss based on either the diffraction angle over the obstruction, or depending on how you have these clutter switches set, it may pass through the clutter instead. For the 3.6 gigahertz and mmWave cases, we recommend always using this add clutter height to terrain height option, which will treat the clutter data as a solid obstruction to be diffracted over, rather than allowing any propagation through that clutter. And especially for the mmWave case, that's much more appropriate than doing a pass-through clutter loss or a flat margin type clutter loss. Some other alternatives to Anderson 2D, let's say, for example, if you do not have a detailed clutter data set and you want to do a reasonable estimate of coverage anyway, the 3GPP forum has published a propagation model specifically for 5G that has a few different categories of propagation and is essentially an empirical distance-based model. And we have implemented that in Signal Pro so that if, you know, for example, if you're still waiting to get higher resolution data and you need an initial count of towers, this is a way to arrive at that estimate. EDX also has offered ray tracing models for decades that will leverage 3D data and do a full ray tracing type of propagation evaluation. And that's sort of what I would call a Cadillac alternative. It's really most relevant and most appropriate in dense urban core environments where the dominant propagation channels are due to the faces of tall buildings. In the suburban and rural case, this ray tracing approach is really not applicable and not necessary for most use cases. The last point I wanted to make here is about atmospheric absorption. And specifically when you've gotten up to the mmWave frequency band, it is appropriate to include some atmospheric absorption, and you can just choose a vapor density level here to, you know, depending on whether your air is normally dry in that market or if you have high humidity, and a climate type as well. And that will apply some additional loss, even just over free space, just for O2 absorption. That's too far there. So I'd like to get into discussing the different data set options that we're focused on here today, and the use cases that they're most applicable for. What I've got here is the 2D clutter. So this is a flat grid clutter data set where we have categories such as developed low intensity, developed medium intensity, forested, etc. And each of those categories has a height associated with it here. Let me go ahead and I'll jump into Signal Pro. And if I look under my propagation models here, we have this attenuation file that is associated with the 2D clutter data set that gives the different categories and the average height that's going to be associated with that category. Now, when using a 2D data set in your model, all of the clutter is assumed to be the height. You know, each category has this height, and the clutter will always be assumed to be that height for purposes of diffracting over or propagating through. At frequency bands lower than 1 gigahertz, the pass-through attenuation can be very appropriate and give you a nice adjustable way to apply clutter loss for propagation through foliage and things like that. If we're looking at the millimeter wave cases or 3.6 gigahertz cases, it's not really appropriate. You won't see propagation through foliage, and so we don't use this pass-through clutter loss. We use the add clutter height to terrain height instead. And in the 2D case, it's critically important to make sure that you go in and adjust these height values for the market in question. Again, these height values started out much higher when I started this project up. And for this particular project, I adjusted them down based on observations I made of this market area and the average height of foliage and the average height of buildings within these residential subdivisions here. So you can see I've got a bunch of subdivisions of houses that all have fairly mature trees. And so I took a look both on Google Earth and found some average heights for the area and then applied those to my different land use categories here. And these categories you can see at the bottom of the screen here. I've got residential, shrub and scrub, developed low and medium intensity, etc. And so I've applied what I think are good conservative height values for each of these clutter categories. And that gives me the clutter height map that I see here. And you can see the area that is transparent here are areas where the height is less than 1 meter, the height of the clutter. And so these represent open areas where I could get good line of sight connection between assets. And then the height of the clutter here for these subdivisions is well represented. And you can see I've got, because this is the hybrid clutter data, I've got the streets and roads have been carved out, parking lots, and for example, the country club golf course here have been carved out as open space. And I've also got some individual building footprints. The mall up here in the top right corner, I've got the actual building footprint categorized as developed high intensity or buildings for a lot of these larger structures here. And so this is a perfectly appropriate approach for initial dimensioning or certainly planning 3.6 gigahertz networks. This can be a good, affordable way to start your design or even produce a finalized design, especially if your towers tend to be substantially higher than the surrounding clutter. You know, if I've got a transmitter here and I'll look at the 3.6 gigahertz case, and let's say I have a subscriber out here and I want to know if I can get connection. I can run a profile, and assuming a subscriber that's 4 meters off the ground here, I can see that the reason I won't have connection here is because of this area of developed high intensity clutter along the path, and that's blocking my line of sight signal. But maybe if I get closer in somewhere like over here, oops, and run that same profile again, you can see I've got a line of sight path, and this clutter really doesn't rise above 1 meter in height along the entire path. So I've got a nice reliable link here. And so when we run the propagation model, either for an area coverage or a fixed point to multi-point or a meshing design, the connectivity is established by these average clutter heights that I've adjusted for my market. And especially if I have tall towers or subscribers that are fixed subscribers that are up above the clutter, this may be a perfectly sufficient approach, especially for the 3.6 gigahertz band. Let me go ahead and switch over now to a project that uses the 10 meter 2.5D data. So if I drop over here to my 10 meter project with heights, I've got the same display set up here where you can see the legend here has the height of the clutter. And in this case, we've got a 10 meter clutter grid, and let me go ahead and show the land use categories first. I've got categories such as grassland agriculture, which you can see down in the status bar here, or forested dense vegetation, or residential with trees. And then up here where the mall is, I've got commercial, industrial, etc. And you notice all of my open in urban space has been categorized as well. So things like parking lots and open space are very well represented within the data set. And the real picture emerges when I show my clutter height. Now, in this case, for the 2.5D data, the height of the clutter at each grid point, or in each bin, if you say it that way, has been measured based on stereoscopic imagery or LiDAR. And Andy, maybe you could speak to how this stuff is gathered at the end for me. But each clutter data point has the type associated, and then also the actual height for that 10 meter wide grid bin. And that height has been averaged for that bin. And so we can see my streets and roads have been carved out, but there are places where the foliage may actually overhang in the street a little bit. And those are well represented within the data. And over here where I've got some taller areas of forested vegetation, you can see that the heights of those treed areas have been measured. And so even within this forested category, I've got different heights for that clutter. And that just means that, again, if I want to evaluate link paths here, and so I'll go ahead and select my 3.6 gigahertz link again and do my profile to point. And let me go ahead and select maybe something down the street here. I want to know if I can connect maybe a block down on the corner of the street. And in this case, I can tell that I have a pretty reliable line of sight path that, and this is really the important part, I have not had to do any adjustment of the heights for these different clutter categories. Because the clutter heights are already defined within their own grid, it does not matter what these heights are within the attenuation file. You know, you can see I've got them all set to 0 here, because the height of the clutter categories is actually, or the clutter is actually measured for every grid point. And that means that I can take the data and plug it in and start running predictions that will be very reliable without any need for additional model tuning or adjustment or sort of site survey type of work. And that advantage, both in the reliability of your initial design and in terms of sort of time to completion on the design, that can be a huge advantage that pays off in terms of the being able to, for example, quote a lower price on an RFP because you've done a more efficient design based on the actual heights of the clutter rather than based on your estimates of the clutter height, which of course have to be somewhat conservative. And so this is a huge improvement over that 2D data where I have to go in and do extra work to set the heights of my clutter categories and make estimates in that way. The next step up that's available is to take this same 2.5D data set and go to an even finer resolution or an even finer grid point spacing. Again, in this case, the grid bins are 10 meters wide, and so the height for any one bin can be thought of as an average for the clutter heights across that entire 10-meter area. And so that has the effect of effectively smoothing the clutter a little bit. And especially for the 3.6 gigahertz band, this is really plenty of detail because any obstruction that's too narrow is not really going to block the signal in an appreciable way at that band anyway. But when we go to millimeter wave, if we're talking about 40 gigahertz or 60 gigahertz, then even the top of a tree sticking up into the line of sight path can be a substantial source of path loss. And in those cases where you really need very fine resolution in the heights, we've actually got another option we can offer through EGS that bumps the resolution all the way down to 2 meters. And so again, this is the same display setup. I've got my heights and the colors associated with them down here at the lower left. And you can see that additional resolution offered by the 2 meter data set does show a lot more granularity in terms of where the really tall trees are and where there are areas that the trees have not grown in quite as much. And especially when we get down into a rural subdivision here, you can see that the individual houses and the foliage around the houses are even represented in fairly fine detail, so that if we needed to distribute millimeter wave links to the very tops of these houses or from one utility pole to the next through this residential area, that sort of application or that sort of use case, we can plan in a very detailed way here with this data. And again, no adjustment is needed of these heights. I can just plug this data in and start designing and have a high degree of confidence that the link reliabilities that I predict are going to be largely what I find in the field. Of course, with any RF planning and with any data set, there's always the rollout period where you go out and start building these things and find where, for example, trees have been cut down or trees have grown up or a building has been put up and those sorts of things. So there's always some amount of redesign and re-engineering in any network. And for millimeter wave deployments, especially, given the high number of assets that are going to be involved, fixed subscribers on homes or microcell base stations, with that high number of assets, it's going to be very important that the initial design be as close to the finalized design as possible. We really want to minimize that re-engineering time and truck rolls out to these sites. And by bringing in a highly granular data set that includes the heights along the path, there's no need for tuning, and there's no need for sort of site survey work to go out and validate those heights. And that not only speeds the time to market, but also your confidence in the prediction. And just to give you the visual comparison one more time here, let me go back to my slide deck, and I'll go ahead and cycle these through so that you can see them next to each other. Here I've got the 2D high resolution clutter, such as the EGS hybrid or our offering in the EDX Cirrus subscription data. And that's 2D with clutter height estimates. And here's the 2.5D clutter with the clutter heights already set. And this is at a 10-meter resolution. And then if we go to the 2-meter resolution from this, again, this is sort of the Cadillac data set where the clutter heights are so granular that you can see individual building footprints and individual areas of foliage. And this would be appropriate for mission critical design or millimeter wave design that like fixed backhaul and that sort of thing, where you really need to design very high reliability links for a small area. If you need to cover a much larger area, this type of data may be cost prohibitive, especially depending on what stage of the project you're in. And so this 2.5D clutter with the 10-meter clutter and heights may be a great middle of the road that still gives you a measured height for each bin so that there's no adjustment needed of the heights, but it's still affordable enough to be able to cover large surface areas and do point to multi-point planning with a high degree of confidence. So again, there's the hybrid 2D data, and then 10-meter with heights and 2.5-meter with heights. And you can see how the additional granularity would really be critical for millimeter wave design, especially if those millimeter wave links are down at utility pole height within this clutter. Now, if we're doing millimeter wave backhaul links from, let's say, a cell tower to a backhaul site, then this 2D clutter approach may still be appropriate. If your tower heights are substantially elevated above the clutter, then an estimate of the clutter heights may be sufficient, and it's going to be terrain effects that really dominate whether or not a path has line of sight. However, if your assets are coming down closer to the height of that clutter, and you don't have the ability to go in and adjust those average clutter heights, then this 10-meter 2.5D product may be sort of a perfect fit. And there's the 2-meter again. So a couple conclusions I wanted to leave you with before we open it up to questions. The main points are here that the geodata you use to plan 5G projects, there really is not one correct data set to use. It depends on the use case that you're trying to support and the frequency bands that you'll be utilizing within 5G. And the really critical frequency bands are the 3.6 gigahertz, and then especially the millimeter wave is very, very line of sight dependent. And so if you're using 2D data, extra care needs to be taken to adjust those clutter heights. But if you need a middle of the road between 3D data and 2D data, this 2.5D clutter data product is dramatically less expensive than 3D data, and all of the detail in height is still there, just at a 10-meter resolution. And so that can be a very affordable way to cover large market areas with a high level of confidence about the clutter height along those paths. And finally, EDX's, excuse me one second, losing my voice. EDX's support team is really happy to help you weigh the options and find the best geodata option and propagation model choices to support the use case that you're building. For our Signal Pro users, we're very interested in how you're applying the tool, especially to these 3.6 gigahertz and millimeter wave use cases, and what sorts of use cases you're being asked to model. And so please do feel free to reach out to support or reach out to me directly just to chat about the projects that you're currently building and what geodata and propagation model options you're using with them. Again, you can contact us here at EDX through sales@edx.com. And of course, if you're already a Signal Pro user, you can always submit a ticket through our customer support portal to get someone talking with you right away about your project. And also, I've got Andy's contact information here at EGS Technologies again. We're happy to partner with EGS Technologies, and we've got a great history with them as a company and their geodata products. So I encourage you to reach out to Andy if you have any questions or a project area that you're looking at. I myself have one question before I turn it over to Rory for other questions. Andy, could you clarify, in the case of the 10-meter 2.5D data, how are those heights usually measured in order to build those into the product?
I'd be happy to answer that, Brian. Thank you. The 10-meter clutter height data, as you'd mentioned during your presentation, is an average height. So if you imagine any 10-meter raster bin, you could have features like a portion of a tree, part of a building, a little bit of a lawn next to it, all included in that 10-meter area. So the way that the data is measured, it's not a LiDAR-based product. It's typically an autocorrelated database. It uses some stereo in order to be able to derive that, and it is truly considered an average height. So if you have part of a tree that might be, let's say, 15 meters high, a home that might be 12 meters high, and part of the ground that might be flat or 0 meters, you may end up with an average height of let's say 8 meters. But again, it's not perfect. You know, the granularity, the 10-meter granularity allows you to literally put a school bus, drive a school bus or a truck through that literal bin and impact the resolution. So it is considered an average. Clients can expect an accuracy of around 3 meters, give or take, in the Z. Sometimes it's a little higher accuracy. It's very rarely any worse than that. But as you'd mentioned, it's really meant to be a very cost-effective way to get a Z component within a database that will give users the ability, literally nationally, regionally, or locally, being able to do a fairly accurate RF calculation for their predictive needs.
Great. Thanks for describing that. And is that usually done with stereoscopic imagery or LiDAR or some combination?
Well, I could tell you it's not done with LiDAR. You know, LiDAR is getting a lot of press lately, and LiDAR is a great product. And for those who are not familiar with LiDAR, it's basically a light, a radar that LiDAR is put into the belly of an aircraft, it's flown over a target region, and signal is sent down outside of the belly of the aircraft, and it reflects back up. And it's done at a very high granularity, often at sub-meter granularity. The problem with LiDAR is it often loses its way in areas that have what I'll call reflective homogeneity. So if you imagine you're flying over a forest preserve or a large forested area, you'll end up with quite a bit of error in a LiDAR database. And so that needs to be post-processed. And while LiDAR does offer a great source of what I'll call a digital surface model, which is effectively whatever is the bare ground plus whatever are above ground features, it really doesn't offer an ability to accurately define what those features are. So it can't give you that clutter height value that you're seeing here on the screen at 10 meter, or like you see in our 2 meter three-dimensional database. So the data is acquired through stereo autocorrelation is the process that's used. And then there is some post-processing done. So we'll check whatever measurements are autocorrelated against our clutter findings to determine whether or not those heights may need to be post-processed or adjusted.
Gotcha. Yeah, that's a question that I've heard a lot, and like you said, LiDAR has been getting a lot of press, but I have also heard, and I know that some of our users do work with doing a lot of post-processing of LiDAR on their own for small project areas. And so, yeah, I'm glad that you sort of described the difference in the process here and some of the pitfalls of using LiDAR if you're not kind of an expert with it.
Yeah,
so,
if I can expand a little, can I expand a little bit on LiDAR, if you don't mind? It's a great product, and the U.S. government is doing a wonderful job of actually providing a free database to really whoever wants it over the United States. It's somewhat scattered as far as coverage area, but if you're doing a pure line of sight type of analysis, I think LiDAR can be a great source tool for this sort of thing. And I think LiDAR is coming of age as a data source that users can tap into. But again, I want to reiterate the fact that LiDAR really doesn't do a very good job at all of determining clutter or clutter categorizations. And so while we've worked with LiDAR internally and will continue to investigate how we can take advantage of LiDAR, it hasn't really proven itself to be a cost-effective way to tease out specific clutter heights, above ground heights, and clutter categories. We still need to go back to that spectral imagery like we're looking at here in the backdrop of your display, where we can determine what's vegetated, what's open land, what's a building, what might be a paved area. Those sorts of things really do not get defined with a LiDAR-only approach.
Yeah. Okay, thank you. Rory, I can see that some folks have asked some questions here. Actually, maybe I'll just go ahead and direct these back to you if I can, Andy. The question's been asked a couple ways here. If you would give us a rough order of pricing for the 2.5D data versus the 3D data for a urban market, for example?
You know, I can certainly tell you, if you're working within the United States, you're probably looking at, you know, 10 to 20 times more expensive for a typical 2D database versus our archived 10-meter clutter and clutter height database. So there is a significant difference in price. And for any customers that are interested in getting projects priced out, we're happy to propose 2D, 2.5D, or 3D data for your areas of interest. And in those veins, obviously, as your areas get larger in coverage, the price will go up, but your cost per square mile will go down. So if you need a small region, you may pay a much higher price per square mile than if you're looking for a larger area. The other thing that I want to talk about related to pricing, especially in the 3D realm, is the temporal accuracy of the source imagery. So we may have data in archive like we do for, let's say, all of New York City or some of the major metros within the country. But if your project is one where we need to get new imagery, we can either go to, let's say, a 2016 or 2017 source versus a 2019 to 2020 source of imagery. And the cost differential might be 4 times more expensive for the newer imagery versus the older imagery. So that's a component that it needs to be addressed when we talk about getting 3D data for clients. So keep that in mind. It's that concept of temporal accuracy. How recent does my imagery need to be in order to give me the kinds of results that I require or expect from, you know, doing a predictive plan? And also keep in mind that you can mix resolutions. So let's say I'm responsible for covering all of Utah State. You know, maybe I only need 3D data at 2-meter or 1-meter resolution for, you know, Salt Lake City downtown. Possibly 10-meter data for, let's say, Salt Lake City Metro and St. George. And then I can deal with 2D data for the remainder of the state. You know, it really is our goal to try to keep your costs as low as possible, get the highest accuracy data that you need for the regions that you require. So don't be shy about mixing multiple resolutions of databases together to achieve that goal.
Yeah, thanks, Andy. And so to follow up on that pricing question that several people asked, we'll follow up with you over email after this meeting, but please do feel free to reach out to us and let us know, you know, send us a polygon of the area of interest, and we're happy to provide actual pricing as opposed to sort of a vague guideline. Because like Andy said, there are a lot of variables there. There are a couple of technical questions that I can field really quick. One of them asks, can you show the setup for the 2D clutter in the database settings, or does Signal Pro just see it? And that's one of the cool things about using the clutter height data set. Excuse me. All you have to do is have that additional heights folder with the clutter height file in there, and Signal Pro will see that automatically and will interpret both the clutter type categories and their heights correctly and seamlessly. There's no extra setting you have to place. The next question is, which prop model is recommended for 2-meter data at mmWave? And I think that for most mmWave cases, the Anderson 2D model is probably going to be the best, most reliable model. And again, we want to make sure we account for atmospheric absorption if we're working with mmWave. And we want to make sure that the add clutter height to terrain height option is set on and that will make sure that clutter is treated as a hard obstacle to diffract over. And then finally, this clutter exclusion distance is the setback where you're saying, okay, every antenna is going to have this much clear space around it before there is an obstruction. And if you're using 2-meter resolution clutter height data, this value should be set down nice and low so that it's not assuming any free space around the antenna. If there's a chimney or a tree right next to the antenna, we'll just go ahead and assume that that tree is there. Otherwise, if you're using a less granular data set, you can adjust this to sort of back off the severity of diffraction effects for very nearby obstacles. So this switch is always appropriate to use for the mmWave case, and typically Anderson 2D is appropriate. Again, there's a lot of talk about ray tracing for mmWave, and that's something that's in EDX's offerings now and is on the roadmap for improvement later. But with ray tracing, that really requires 3D polygon data, and it's just not appropriate for rural or suburban type mmWave planning. Although there was one other question about how to set the clutter height for the trees. If you can see in Google Earth that the tree height is 45 feet and you want to adjust that, how can you adjust it? Well, if I want to work with feet, then the first thing I do is go to my map units and select English units, and that gets me out of using meters and takes me into using feet. And then I would go in here and adjust my attenuation file that comes with, oops, I'm in the wrong project. I need to go to the attenuation file for my 2D clutter here. If I'm adjusting the height of these clutter types, I want to go in to the propagation models. And here I've got the attenuation file that gives the height of these different clutter categories. And I can adjust those here. Let me put myself back in feet again. And so, for example, if I wanted to set the height of the evergreen forested category to 45 feet, I would just highlight this category, set it to 45. And then when you make adjustments on these tables, I like to use the save file as, and I can save a market specific version of the attenuation file, so that if I adjust these heights for one market, I'm not necessarily adjusting them for all of my other projects that use that data. I can keep a special attenuation file for each project and each market. Finally, there's one last question about the ray tracing and when that's scheduled for release. We do have a faster ray tracing model that's on our roadmap, and is the first 2D version of it is scheduled for release soon. I don't have a hard and fast release date on that at this time, but I'm myself hoping for the end of the year. And that gets us through, I think, all of the questions that anyone asked. If there are any follow-up questions, please do feel free to reach out to us at sales@edx.com. And thank you again to Andy Baffis and EGS Technologies for contributing to our discussion here today. And thanks to all of you for joining this webinar.